Let's begin by understanding what warpage means in the context of 3D printing. Warpage is the unintended distortion that occurs when a printed part's corners or edges lift from the build plate during the printing process. This phenomenon is especially common in models with large footprints. Warpage typically starts when the internal stresses within the part exceed the adhesive forces holding it to the bed. The result is a part that doesn't match the intended design, often with visible lifting or curling at the edges. Recognizing these visual cues early can help you take corrective action before the print fails. Warpage is fundamentally a result of thermal deformation. As the 3D printer lays down molten plastic, the material expands. When it cools, it contracts. If this cooling happens unevenly, say the upper layers cool faster than the lower layers attached to the heated bed, tension builds up. This tension can pull the edges of the print upward, causing the classic signs of warpage. The root of the problem is non-uniform thermal contraction, which is why temperature management is so critical in 3D printing. To address warpage, it's essential to understand its root causes. The main culprit is the physics of polymer shrinkage and thermal gradients. As each layer is deposited, the temperature difference between the hot nozzle and the cooler bed creates a thermal gradient. This gradient leads to internal stresses as the material solidifies. The higher the infill density, the greater the warping forces, since more material means more contraction. Recognizing these factors helps in adjusting print settings for better results. Differential shrinkage is a key driver of warpage. When molten plastic is laid down, it starts off expanded due to the heat. As it cools to room temperature, it contracts. If the upper layers cool and shrink faster than the lower layers, the resulting tension pulls the edges upward. This effect is amplified by a significant temperature delta between the nozzle and the bed, as well as by the internal stress from molecular chains pulling as they solidify. Managing these variables is crucial for minimizing warpage. Environmental factors can also trigger warpage. Sudden drafts from air conditioning or open windows can cause localized rapid cooling, leading to asymmetric stress in the print. A cold build plate where the bed temperature is too low prevents the first layer from staying above the glass transition point, making it more likely to detach. Additionally, excessive use of cooling fans, especially at 100% on the first layers, can prematurely solidify the foundation, increasing the risk of warpage. Not all filaments are created equal when it comes to warpage risk. Some materials are much more sensitive to thermal stress and shrinkage. For example, ABS has a high shrinkage rate and often requires a heated chamber to print successfully. Nylon is extremely prone to warping and is also highly sensitive to moisture. Polycarbonate is strong but generates immense internal stress. On the other hand, PLA is considered the gold standard for low warpage printing, making it a popular choice for beginners. Each filament type has a unique shrinkage coefficient, which determines how much it contracts as it cools. Materials with high semicrystallinity or large thermal expansion coefficients are considered high risk for warpage. For instance, ABS and nylon are notorious for their high shrinkage, while PLA has a much lower coefficient, making it more forgiving. Understanding these properties helps you choose the right material for your project and adjust your print settings accordingly. Warpage isn't just an aesthetic issue, it can lead to serious mechanical failures. When thermal stress is unmanaged, it can cause layer delamination where layers split apart due to vertical tension. Dimensional errors are also common, resulting in parts that don't fit into assemblies or enclosures as intended. Additionally, warpage weakens the Z-axis, reducing the bond strength between layers and compromising the overall structural integrity of the print. To put things into perspective, let's look at some shrinkage benchmarks. Nylon can shrink by as much as 1.5%, ABS by 0.8%, and PLA by only 0.2%. This means that nylon and polycarbonate are at high risk for extreme warpage, while PETG and ABS present a moderate, more manageable risk. PLA remains the safest bet for minimizing warpage, especially for precision parts. Knowing these benchmarks can guide your material selection for critical projects. So how do professionals tackle warpage? The solution matrix involves three main strategies: improving adhesion, controlling the environment, and optimizing geometry. Heated enclosures trap ambient heat to slow down cooling, reducing thermal gradients. Advanced adhesives like PEI sheets or specialized glues enhance bed adhesion. Brims and rafts act as sacrificial structures, anchoring the corners and preventing them from lifting. Combining these methods can dramatically improve print quality. Optimizing your print settings is essential for minimizing warpage. Start with the first layer. Reduce print speed to around 20 ms and increase the initial layer height to 120% for maximum bed contact. When designing parts, avoid sharp 90-degree corners. Instead, use fillets or mouse ears to distribute stress more evenly. For cooling fans, disable them for the first 3-5 layers and keep them at 0-30% for high-temperature material. These small tweaks can make a big difference. First layer is the foundation of your print. Ensuring it adheres well to the bed is critical for preventing warpage. Use a clean level build plate and consider using adhesives like glue stick or PEI sheets for extra grip. A thicker first layer and slower print speed help the material squish into the bed, improving adhesion. Remember, a strong first layer sets the stage for a successful print. Smart part design can greatly reduce warpage risk. Avoid sharp corners, which concentrate stress and are more likely to lift. Instead, use rounded edges or add mouse ears, small discs at the corners to help anchor the part. Also, consider the orientation of your print. Sometimes rotating the part or splitting it into smaller sections can help manage thermal stress more effectively. Cooling fans are a double-edged sword in 3D printing. While they help solidify layers, using them too aggressively, especially on the first few layers, can cause premature solidification and increase warpage risk. For high-temperature materials, keep the fan off for the first 3-5 layers, then set it to a low speed. This approach allows the base to adhere firmly before introducing rapid cooling. Summary: mastering thermal management is the key to successful 3D printing. By understanding the causes of warpage and implementing engineering-grade solutions, you can produce parts that are both visually appealing and structurally sound. Remember to optimize your print settings, choose the right materials, and control your environment for the best results. With these strategies, you'll be well equipped to tackle warpage and achieve perfect prints every time.